So if I put this into the oven and turn the oven on, what's going to happen?
Explode.
What was that?
Explode.
Explode? I hope not.
What's it like?
Bubble?
Isn't that like, what is that?
It's I assume it's aluminum, but it could be steel. Actually, it feels too heavy to be aluminum.
Don't microwave, don't catch fire.
True. Let's say just a normal, conventional oven.
It's gonna heat up. Yeah.
Okay, one thing it'll heat up. So if I put energy into the system, it will get hotter. So, energy, and it's going to get hotter. What does it mean in terms of the atoms in here? This thing is made up of atoms. What does it mean for something to get hotter?
Don't they expand?
What?
They
Yeah.
speed up.
You're almost there. The atoms themselves don't expand.
The molecules expand.
Probably as much as the atoms do. It's not the molecules. I'm going to go with the spirit of what you're saying there. The molecules will get farther apart from each other. So the material expands. The molecules themselves don't really expand. It's just the space between them. So I put energy in. It's going to get hotter. And then for most materials, it expands. Why would they expand? So let's think about the molecules. I put energy into the molecule. What's it going to do? Pardon?
Warm up. Heat up.
What does that mean, though, in terms of a molecule?
They move apart.
All right, suppose we were all crammed into a corner. Probably uncomfortable. If we all of a sudden we had more energy, what would we do? Or let's say you're sitting where you are. Let's not put ourselves in a corner yet. You're where you are. If you had more energy, what would you be doing?
Yep. Moving.
Yeah, you'll move around more. So as you put energy in, you move around more. So now let's cram ourselves into the corner, and we each get this burst of energy. What are we going to do?
Move away.
Well, yes, we will move around, and then it'll basically force us to move away from each other. Because if you're crammed in there, there's really only so much you can do. So you start pushing people out of the way, pushing molecules out of the way. So heating up, they make something hotter. Putting energy into the system. Basically, I'm causing a change in the kinetic energy. Expanding is a consequence of that, but expanding is I'm changing the position, relative position of them. This is a change in potential energy. Our old friends, kinetic and potential. All right, so let's say I keep heating it up. I got an industrial oven. I put the steel rod in there, or whatever material this is, into the oven. It will start to heat up. So it's like keep heating it up. What's going to happen?
Gonna melt.
Yeah. So at some point, it will change phase. So potentially it will change phase. And when I say change phase, the three basic phases are solid, liquid, gas. Is there another phase? Well, yes, there are. Name another phase besides solid, liquid, and gas. There's the fourth one. Some TVs use it. Some lights use it. core of the earth uses it. It looked like you were forming the first letter at least.
Say mass.
Is steam a gas?
Steam is, yes, steam is a gas. Plasma? This is not blood plasma. I eventually read something that talked about how it got its name. The person who called this substance plasma said it reminded him of blood plasma. So that's why he gave it the same name. Basically, plasma, it's so hot that the electrons can't stay attached to the nucleus, and so you just get this sea of nuclei and electrons sort of floating around out there. And then if you go to Wikipedia, there's like a dozen more different phases. These are the big three right here. That's the next one, probably in terms of what you might be exposed to. And then you have two types of solids, crystalline solids and non-crystalline solids. Glass is a non-crystalline solid. It will, given time, flow. Bose-Einstein condensates is another form of matter, and so on. All right, so if you do the change of phase, basically I've got these atoms, I'm putting the energy into it, it's getting hotter, they're moving around, getting farther apart from each other. When you do the change of phase, it doesn't get hotter when it changes phase, it just gets even farther apart. So solids, they'll be like this, then they'll start moving around, eventually they'll get to the point where they're farther apart, so we're down to a liquid, and then you put more energy into it, they'll be moving around even more, and then they get far enough apart, and we're not dealing with a gas. So if it changes phases, what we're dealing with here is a change in potential energy. Then if you keep putting energy into it, then it'll start getting hotter again, and we're back to changing kinetic. So all of this stuff that we're dealing with here in thermodynamics is just, bless you, energy being transferred from one thing to another. Unfortunately, thermodynamics was designed slightly differently, or was sort of parallel development with a lot of the other language, and so they came up with their own language. You might hear a reference to thermal energy. Thermal energy is just a form of kinetic. Chemical energy, just a form of potential. Now, if I take energy out, then it can still change phase. I can freeze water. It'll get colder, and most liquids will contract. What is something that won't expand when heated? Or will expand when cooled? Most of you have dealt with this in your life. Matter of fact, some of you have even brought examples into class.
Is it your skin?
Say it again?
Skin?
Oh, I wouldn't think about it. I don't think skin does, but I don't know about skin. When it's cold,
Like water and ice.
yeah, that's what I was thinking of. I don't think about skin. Yeah, water will, at a certain point, will start to expand, and that's one of the reasons it floats. And I think Wikipedia's got a list of like 6 substances, of which water is the only one I'd ever heard of before. All right, so let's first start out with, well, actually before that. thermodynamics, the first law of thermodynamics. When you're dealing with the laws of thermodynamics, a lot of it is statistically based. So, you're playing the odds. There are several different forms of the first law of thermodynamics. And I've seen textbooks jump through hoops to try to explain it. They give different situations and it all just comes down to energy. I have a box with a certain amount of energy into it, which is called E sub I for initial energy. I'm going to put energy into the system, and that when I put energy in, I can heat it up, in which case we're dealing with thermodynamics. I can lift it up, putting potential energy into it, in which case it's a mechanics problem, but I put energy in. Some energy is going to come out of it. If I heat up something in the oven, I'm definitely putting energy into it. I pull it out of the oven, I put my hand near it, it's hot, energy's coming out. So I start out with a certain amount of energy, I put energy in, I take energy out, and then I'm left, it has a certain amount of energy in the end. So basically, I have a certain amount of final energy, whether it's kinetic or potential. So I start out with a certain amount of initial energy. I stick energy into it. And then in the end, I have a certain amount of final energy plus the energy that left. I start with something to put stuff in, stuff comes out, I'm left with something. That is the first law of thermodynamics. However, you will never see it written that way. Instead of the energy out, they will call that work. So oftentimes they'll just call that work. Energy initial and final there, so if I subtract that from both sides, I get the final energy minus the initial energy. That is the change in energy. And then I have energy going in. It's thermodynamics. You don't want it to be so simple as to just call it energy coming in. They call it heat. And of course, the letter Q for heat. So the energy going into the system is equal to the change in energy plus the work done by the system. And if you followed along, you're going, okay, sure, we renamed some stuff, but it's, sure. I start with energy, put energy in, energy comes out, and I'm left with something. However, when you're dealing with thermodynamics, there are two conventions. What I did is I looked at the box. I started out with a box there, it's surrounded by something, energy comes in, energy's out. Some thermodynamics, they decide, you know what? I don't want to look at the box, I want to look at the environment. So if I put a hot cube in the middle of the room, I can look at the whole thing from the point of view of the cube, which is what I did here, or I can look at the whole thing from the point of view of the room. In which case, I have energy going into the room is equal to the change in energy minus the work being done to the room.
So is the Q heat or energy?
Q is heat, which is a form of energy that's being transferred between objects. Both of these say the same thing. And if you ever look at a thermodynamics textbook, so you're just excited by thermodynamics and you're thinking, yes, that is what I want to read, or I need to fall asleep, let me pull out a thermodynamics textbook. Usually the first parts of the textbook is explaining which conventions they're using. I tend to do this one. Looking in terms of, I put a cube in the room, I'm looking at the energy exchanges with the cube, and not worrying about the room as much. I don't know why they just can't settle upon one. Like with RAP, East Coast, West Coast, probably something like that. All right, so thermodynamics, we're dealing with energy going in, going out. So we need to somehow figure out, if I'm putting energy in, how hot is it gonna get? So I take a block. I stick energy into it. Let's just assume for right now, nothing's leaving it. So all the energy I put into it is going into the block. What do you think is gonna affect how much how hot it's gonna get?
How much energy you're putting in?
Okay. There's one. What else do you think is going to affect it?
How long the energy is in?
Oh, how long you're putting in? I sort of lump that into the total amount of energy put in. If no energy is escaping, I put all the energy into the cube and nothing's escaping, then the primary issue is just how much energy am I putting in. If energy is escaping, then I'd probably have to bring time into it. But we're dealing with a nice, simple, ideal, I got a cube, I'm putting energy in, nothing's escaping.
The box, how the cube, how big it is?
Ah, size of the box, okay? Put that over here, volume. It's something that's gonna be related to volume, but not the volume itself.
Is there something else? Is there anything else?
Yes,
There is?
yes.
Is it the amount of energy that comes out of the cube?
We're making the assumption nothing's coming out right now. Yes, that would affect it, and then we'd have to bring time into it also. Keeping it simple.
So the question is, we're trying to figure out how hot it gets?
Yeah, what's going to affect it? So far, we've had size of the object, and it's indirectly related to size, and the amount of energy that you stick in.
Temperature? No.
What do you mean by that?
Like how much heat?
We're trying to find temperature, so there's going to be an equation which has. So how hot it gets, what we're ultimately looking for is the temperature change, or we can calculate how much the temperature is going to change. And if I know the initial temperature, I can therefore find the final temperature.
Is it like not how big the box is, but like how thick it is? Does that have to do with it?
How thick it is,
Yeah.
I still lump that under volume. But, okay, I'm gonna put you out of your misery on part of this. It's actually the mass, not the volume. That's the important part. So mass. And there's one other crucial factor that's going to affect.
Is it what it's made out of, the box?
Yes, the material itself. That's the relationship that we're talking about here. This C, of course, has a name. It's called the specific heat. Specific. And it is material dependent. It can be derived in certain situations, but it's usually found experimentally. So if I have a material, so let's talk about units here. Q is energy. More specifically, it's heat. And when we're talking about heat, we're talking specifically about energy that's being transferred because of a difference in temperature. So if I put a cold block into hot water, the block will get hotter. That's energy going in because of the difference in temperature. If I take a hot block and stuck it in the freezer, I have energy leaving. That's heat. So if heat is just a type of energy here, what would the units be? Units of energy. What are they? SI units of energy.
Joules?
Yes. All right, so Q would be in joules. Mass. What are the units of mass? Trying to figure out what the units of specific heat are. And units of temperature?
Celsius.
Fahrenheit?
In the international standard is not Fahrenheit. The world refuses to conform to us. Degrees Celsius or Kelvin.
Oh.
I'm going to put in Kelvin here. You'll often see degrees Celsius as well, just as often as you'll see Kelvin. This is Kelvin.
That's a unit of temperature?
Yes, it is.
So let's talk a little bit about Kelvin.
Lord Kelvin. That's the person. If I take, let's say, I seal this up, so I've got a certain amount of gas in here. Particles are moving around, and I stick this into a freezer. What's going to happen to the particles?
I'll freeze.
And what does that mean?
They get closer.
Okay. So what about their movement?
Slow down.
Okay. As I make it colder and colder and colder, what's going to happen?